the topic we're looking at today is curve sketching and function analysis. This corresponds to section 4.6 in the textbook. So, going well on the way to becoming walking, talking, graphing calculators, okay? So, not only can you graph an approximation, a good enough graph, but can you graph an accurate, unique graph of a function. So kind of doing a quick review based on these graph examples you have, what information can we gather from these graphs? So for each of these, for A through H, looking at the graph, can you determine whether each point in the question is a critical point, a relative minimax, or an inflection point? So kind of going through, putting X where you think something is. So graph A, that point. That smooth curve, it's going up, topping out, coming back down. The derivative equals 0. So critical point, that's really thick, there we go. Relative min, I don't think so. But relative maximum, yeah, we'll go with that. And then, not an inflection point. The concavity doesn't change at that position. The whole graph is concave down, right? Graph B is the critical point where the derivative equals 0 at that point, smooth curve, and there's a turning point from decreasing to increasing behavior. So critical point. And looking at all these, I think we can say these are all critical points. They all have a derivative that equals 0 or derivative that's undefined, either due to a vertical tangent line or a sharp corner. So go ahead and mark all of these as critical ones. Going back to B, you see decreasing to increasing behavior, smooth curve, relative minimum, and we don't see a change in concavity. It's not an inflection point. Graph C, we see decreasing to decreasing behavior, so not a maximum min. We also see, can just zoom in on it, we see concave up, then switches to concave down. So we see a change in concavity at that point. So we can say that is, where's my typing? Here we go. So we can say example C is a point of inflection. And graph point D, we have the same kind of shape as C, critical number, but not a maximum min. There's a change in concavity, so you can see critical inflection point for that also. So take a moment on your own, pause the video, look at E through H, and then come back to it. So at point E, critical point, we have derivative not existing because of the sharp corner. We have increasing to decreasing behavior, and both halves are concave down. So we see in E, kind of traced over here, we have a maximum. In F, kind of the same thing, but in reverse, sharp corner, decreasing to increasing. So a relative minimum. G, we see a change in concavity. So that being an inflection point. And H, we also see in H a not a maximum min, but a change in concavity. So also an inflection point. Now reading graph as it is and kind of determining special points is good, but given a graph of any function or its derivative or its second derivative, could you make a possible graph of any other state of that function, the function itself or first or second derivative? So example 2, given the first derivative, we see the first derivative is positive. That means we have a positive slope. And the first derivative is constant, so it's constantly a positive slope. So a constant slope, we have a linear function that is increasing. Now what we don't know, kind of come over here. What we don't know is where the line is placed. All we know is the slope. We don't have an initial condition or a point on the graph. So a slope of 2. That's all we know. So up 2 over 1, up 2, I can take my scale, up 2 over 1, up 2 over 1, up 2 over 1. And I missed just about all the points. That's better. I'll kind of cheat, move that point down. Okay, now again, we only know the slope, we don't know its placement on the graph. So this whole line could be up here, could be down here, could be anywhere on this y-axis, but we don't know. We don't have an initial condition. So again, it's only a possible graph of f(x). Example B, we see the slope is negative then positive. A negative slope means decreasing behavior. A positive slope means increasing behavior. And we know the change in that behavior happens at the y-axis at x equals 0. So we need a negative slope, but getting less negative as you get closer to the y-axis. After the y-axis, a positive slope gets more positive. So a negative slope that gets less negative. So a negative slope that gets less negative with time, kind of take the slope and bend it down, make it concave up. We're going to get something like this. Decreasing behavior over here, increasing behavior over here, and kind of a gradual change from decreasing to 0, because right here we have a slope of 0, and then going to increasing behavior. For the rest of the examples, example 2, take a look at those, sketch possible graphs, then check my completed notes online. And for the rest of the section, analyzing graphs of functions. So maxes, mins, intercepts, domain, discontinuities, vertical asymptotes, increasing, decreasing behavior, concavity, minimums, maximums, points of inflection. So really taking everything we've been looking at all semester, every little thing we're looking at, putting all together into curve sketching, making a very accurate graph of a function without a graphing calculator. So take a look at the examples A and example B. Don't use a calculator if you can avoid it. Try to do them by hand. When you're done, check my complete notes online.